let's say that we have a rectangular slab with a cross-sectional area so large that we can negate any of its edges, which means that we do not have to worry about variations in the y and the z direction. So there's just the x direction. On one side of the slab, it's completely insulated. On the other, it's exposed to air at the temperature of 20 degrees Celsius. And this slab is 80 degrees Celsius. The slab is initially uniformly 80 degrees Celsius, so our initial condition can be written as the temperature at x of 0, where we can label this side as 0 and this side as L, is equal to 80 degrees Celsius. As we said before, one side is completely insulated, which means that the temperature gradient at this side has to be equal to 0. That can be written out as the temperature gradient at x is equal to 0, this side, right, is equal to 0. This is known as a Newman boundary condition. If we look at the slab once again, you'll notice that this side is not insulated at all, at L. So the heat must be leaving somehow, by convection. Q of convection, we'll call this heat leaving by convection. This can be written as Q, heat convection, is equal to the thermal conductivity multiplied by the temperature gradient. Because that's side L, we'll say that x is equal to L. While we're losing heat from convection on this side, we are also losing heat through conduction in the slab. So heat of conduction, this heat of conduction is equal to the thermal conductivity, once again, multiplied by the temperature at L, length L, over time, minus the temperature as we move away from the slab. Heat leaves the surface of the slab via convection, and that is proportional to the heat loss as it moves through the slab via conduction. So this equation can be written as the thermal conductivity of the temperature gradient at distance L is equal to the thermal conductivity of the temperature at length L time T minus the temperature as we move away from the slab. The evolution of temperature within the slab is governed by a one-dimensional heat diffusion equation that can be written as the gradient of temperature, or the rate of temperature over time, is equal to the thermal diffusivity multiplied by its second derivative. Now this, we can learn a lot. So as time goes on, the physical properties of the temperature, the slope at the perfectly insulated side will remain at 0, because the slope will not change. However, on the side that is not insulated, the slope will slowly begin to lessen as the temperature becomes the same as the air outside. So now we have a steeper slope. As time progresses, the profile becomes more nonlinear, and eventually it will reach a steady state shape. This is because the heat conduction through the slab and heat convection from the slab to the surface will slowly balance. If the convection coefficient, the thermal conductivity, is high, you will find that the steady state profile will become a linear temperature gradient. If you look at the diagram, a horizontal line will slowly dip downwards as it is more exposed to the air as x becomes L, until it reaches the side that is exposed to the air. And this will become temperature profile throughout the entire slab. Given the initial and boundary conditions, as well as the diffusion equations, you will find that you will be able to solve this problem analytically or mathematically, depending on if there are actual numbers to this problem. Let's imagine a coffee cup problem so we can sketch a temperature profile. This coffee cup is made of glass in this situation, and it holds a hot liquid inside, 90 degrees. Now, when you touch the coffee cup, it's very hot. So you put an insulator over top. That way, when you hold the coffee cup, your hand doesn't get hurt. We can draw this in a more simplified version with your liquid being right here, your glass mug right here, and your insulator here. And then we just have air because the insulator is exposed to air. Now, if we're assuming quasi-steady state, the coffee temperature will not decrease appreciably over the time we're looking at. And our coffee right now, or our liquid, is 90 degrees Celsius, while the air outside of the cup is 20 degrees Celsius. And what we are attempting to do is sketch a temperature profile over all of these materials. However that may be, for example, it could look like this. That's not how it's going to look like, but it could be that. Now, when we draw a temperature profile, let's start off with the liquid. It is 90 degrees Celsius, right? And it's a constant bulk source of heat. When it reaches the glass, it will slightly decrease, but not too much. The glass isn't insulated, it's not going to decrease the temperature by much. Now, the insulator, if it's effective, will decrease the temperature heavily. But once it gets to air, because of convection, heat loss by convection, the temperature will likely not decrease by much. So how am I able to assume this temperature profile? Well, let's start by So how am I able to assume this temperature profile? Well, let's first start by labeling our variables. We'll call this T1, temperature 1, T2, temperature 2, temperature 3. This can be the temperature of the coffee, TC, and this can be temperature of the air. Now we know that the insulation and the glass are losing heat by conduction, while the air and the liquid are losing heat because of convection. Through Fourier's law, we know that the equation for heat loss by conduction is equal to our thermal conductivity multiplied by our area multiplied by the temperature difference. And in this case, it will also be over a certain length because there's a length of glass that the temperature is decreasing through and a length of insulation that this temperature is decreasing from. So for our heat loss of glass, we can say that the thermal conductivity of glass multiplied by the area multiplied by T1 minus T2 over our length is equal to the heat loss via conduction. Repeat this process with our insulation. Our thermal conductivity of our insulation multiplied by the area, T2 minus T3, over the length of the insulation, and now we have both heat loss equations. For our heat loss of convection for the liquid and the air, the equation is going to look slightly differently. For our heat loss through the liquid and the air, our equation is going to look slightly different. We will have our heat loss for our coffee, and that will be the heat transfer coefficient multiplied by the temperature loss, Tc minus T1, not over a length, but you still multiply by an area, and our air will be heat loss The heat loss of our air will be the heat transfer coefficient once again. We'll label this one C and this one A. T3 minus TA multiplied by the area. Temperature of 3 minus the temperature of the air times the area. We can also assume that each of these equations is equal to one another. The heat loss through each of these sections should all equal each other. So let's take each equation and set them equal to one another. We have our glass. We have our insulation. Our coffee. And finally, our air. And there's the equivalent equations. This equation can show us the temperature profile. How, might you ask? Well, each of the thermal conductivities, the heat transfer coefficients, are all different. And so if all of these equations are equal to one another, what has to change? The slope. These slopes will all vary, meaning that each slope over here will vary. Our thermal conductivity for our insulation must be lower than the glass because it conducts heat at a lower rate. So the slope will be larger. And our glass will conduct heat at a higher rate. A thermal conductivity will be higher, which means our slope will be lower. Write that as that. So therefore, the heat loss of our glass, its slope will be lower, smaller, less steep than the slope of our insulation. And that is evident in our temperature profile, where the slope right here is not as shallow, deep, or steep as our insulation. So overall, assuming quasi-steady state conditions, in this scenario, we can assume that this is the general temperature profile of insulation and glass. Let's look at conduction-convection heat transfer through a lens of thermal resistance with regards to our initial coffee cup problem. First, let's start out by writing change in voltage is equal to current multiplied by resistance. This will help us learn the basics for what we are about to know next. If we look back at Fourier's law, you'll remember that our heat loss is equal to our thermal conductivity, we'll ignore the negative for now, multiplied by our change in temperature divided by our length. From here, it's very evident that this change in temperature is synonymous or proportional to our change in voltage. So translating this equation, we will find that our change in temperature is equal to our heat loss multiplied by our length over thermal conductivity. Writing our change in voltage is equal to current multiplied by resistance. It is clear that temperature and voltage are related, our current and our heat loss are related, and our resistance and the length over thermal conductivity are also related. So there's one more variable, but that I forgot for this equation, and that is area. We'll just stick that right in there. Now that we understand that our change in voltage is similar to our change in temperature equation, we can determine how to find the total heat flow of a problem, like our coffee cup problem. How might we do that, you ask? Well, the total resistance of a circuit, as you typically learn in Physics 1, is just the sum of the two or more resistors that are in that circuit as long as they are parallel. And we can rewrite this equation as R is equal to delta V, change in voltage divided by current. But we don't want the resistance. We don't want the total resistance because that would be the total of these variables right here. We want the total heat flow. So let's think about this in terms of current. Well, current is the change in voltage divided by resistance. And that means that the total current must be the inverse of the resistances added together. And we can use this with this equation. So let's rewrite this again, or we can just look over here and look at this equation. Our heat flow is equal to our area multiplied by our thermal conductivity multiplied by our change in temperature divided by our length. And when we rearrange it, it equals this. And now if we look at it in terms of thermal resistance, we can find that our total heat flow, just call it QT, is equal to our change in temperature divided by our length divided by our thermal conductivity multiplied by our area. You can put a negative in here. You don't have to, though. I'm not going to in this problem because it depends on which way you choose to put the x direction. So in this equation, we're going to negate the negative because you'll worry about that depending on which problem you do. Let's apply this to the coffee cup problem. As you see, we have our thermal conductivity, our length. Let me underline this, our thermal conductivity, our area, our length, and our change in temperature right here. And we can use this to find the total heat flow, which would be our change in temperature divided by our length divided by our thermal conductivity multiplied by our area. And that is different for each material. So for our first material, we have our glass, which is T1 minus T2 divided by length of the glass multiplied by, or divided by, our thermal conductivity of our glass multiplied by the area. So we continue on with that. T2 minus T3, temperature 2 minus temperature 3, divided by the length of the insulation, thermal conductivity of the insulation multiplied by the area, Tc, temperature of the coffee, minus temperature of the first sector, heat transfer coefficient, 3 minus Ta, air coefficient, and now we have this massive equation right here. So for this heat transfer process, we can then simplify it by realizing that this change in temperature is just the change in temperature from the coffee all the way to the temperature of the air, which is the temperature to infinity, right? Because the air goes on, we're assuming forever, right? We're assuming there's nothing in its way. So we can just do the change in temperature is temperature of the coffee minus temperature of infinity, divided by 1 divided by area, because each of these has an area in it, multiplied by, oh, forgot to put this one under that, multiplied by our length, the glass, thermal conductivity, glass, length of the insulation, the thermal conductivity insulation, heat transfer coefficient of the coffee and the air. And there we have our general massive equation for the heat transfer process of our coffee cup problem. And if you really want to continue to simplify this, we now have that area times our change in temperature divided by this, we'll call this the ultimate heat coefficient. And I mean, if you want to continue simplifying it, you don't need to put this ultimate heat coefficient in the denominator. You can put it in the numerator because at the end of the day, you've defined that. And this would be our final, T is not squiggly. This would be our final equation for our thermal resistance with relation to our heat transfer process. Our overall heat transfer coefficient multiplied by the area of what we're working with, in this regard it's a coffee cup, multiplied by the temperature change from the first material all the way until the last, which is the air. And this single expression tells us how the geometry, material properties, and surface conditions all affect our heat transfer process. Looking through this process, you can see how each thermal conductivity or length or heat transfer coefficient or area or temperature change might affect the temperature profile. So you can visually see what will happen. And there you have it. There is our heat flow in terms of thermal resistance.